Hello everyone, welcome to MECH 3323 Solid Mechanics Laboratory at UTEP. This is your instructor, Naushad Islam, and today we're going to be going over energy absorbed at fracture. This is going to be a very short lecture focusing on impact tests, types of impact tests, principle of iso tests, and we're going to be talking a little bit about the experiment, the experimental procedure, and the report. Let's talk about impact test. Impact test is basically a destructive test that determines the amount of energy absorbed by material during fracture. Um, Usually in an impact test, you'd have a notched specimen which is fractured using some form of impacting body. During the fracture time, the impacting body loses some of its kinetic energy to the fractured specimen, which is absorbed by the specimen. Um, Now, this energy absorbed is a good indication of a material's toughness. A material's toughness is basically its ability to absorb energy during plastic deformation. So, impact test is a very good tool to tell whether a material is brittle or ductile, because a ductile material can withstand a lot of plastic deformation and can absorb a lot of energy, whereas a brittle material cannot withstand as much as energy and as much as plastic deformation, or can absorb as much as energy as a ductile material. This test can also be used at elevated temperature and also check temperature dependency to see brittle to ductile transition of materials. Because some materials they become ductile as the temperature is increased and they're heated up. So the toughness increases at higher temperatures for those materials. Let's talk about types of impact test. There are several types of impact tests, but we're going to be talking about the two most common types of impact tests, the Charpy test and the ISOT test. They're both similar types of test where you use a notched specimen and usually use a V-notch specimen, and how you do the experiment is you have a pivoting hammer arm which hits your notch specimen and fractures it at a single go. Uh, the only difference between the specimens are how they're supported. On a Charpy test, the specimen would be supported as a three-point bending orientation or simply supported beam orientation. You can see that on the right picture how a Charpy test specimen would be supported uh, during the impact. And for an ISO test, you'd have the specimen as a cantilever orientation. So that's the basic difference between these two tests. And usually on Charpy tests you use V-notch specimen, where in ISO test you could use V-notched, U-notched, or keyhole notch specimens. On For this experiment, we're going to be focusing mainly on ISO tests. Okay, let's talk about the ISOT impact test. So for our case on the ISOT impact test, we're going to be using a V-notch specimen which is going to be gripped vertically and secured firmly on a holding device. And we're going to be using a pivoting hammer arm to fracture the specimen with a single blow. The blow will be struck on the same face where the notched V-notch should be located in, and we're gonna be measuring the energy. So now you can see there's several types of specimens I talked about on the previous slide which we could use, and one thing that you should remember that for a V-notch specimen the notch size would be no more than 2 millimeters, and for any kind of notch the notch size is 2 millimeters, or the notch thickness would be 2 millimeters, and for different type of notch the length can be different. Now you can see on bottom left picture that is a standard IZ impact test specimen dimensions in millimeters. So the when you secure the specimen on the test stand vertically, you'd have the distance between the notch and your top uh, striking position is 22 millimeters. You have to maintain that to get accurate results. So how does an isotope impact test work fundamentally? So you can see that when the hammer is at position 1 or at the initial position before the strike, all the energy on the hammer is potential energy. Now when you let go of the hammer, all that energy transforms into kinetic energy and hits the specimen and fractures it. Now from conservation of energy, if some of the energy is lost, then the hammer would not go to the same position as point 1 or the same height as point 1 um, after hitting the specimen. So you could see that there from the figure that at the initial time the hammer was in H1 position. After striking the specimen, it goes to H2 position. So there's a distance between H1 and H2. Since they're not equal, that means some energy have been lost in the fracture. That is the energy that has been absorbed by our specimen. So how do we calculate that? So the energy absorbed during fracture is equal to mg, that is m is the mass of your hammer and g is the gravitational force times the difference between h1 and h2, the two heights. Now in our case, we do not know what is h1 and h2. However, we know the hammer arm length, that is r. Now from some geometrical calculation, and if we know the angles between how much the hammers traveled from initial position and what was the angle at the initial position and what is the angle after the um, after striking the specimen, we would be able to do some calculations and find out that h1 is basically equals to the length of the hammer arm r plus sine alpha minus 90 degrees, and h2 would be r plus sine beta minus 90 degrees. Um, in any case, if the beta is less than 90 degree, we would get r minus sine 90 minus beta. So the energy absorbed during fracture would be, if you simplify it, you'd get mgr sine alpha minus 90 minus sine beta minus 90. And from there on, you can theoretically calculate how much energy have been absorbed during the fracture. However, during these tests, some energies are also being lost by heat and other forms. So on this experiment, we're gonna be looking into um, calculating that lost energy as well. So the objectives for this experiment are gonna be, we're gonna be using different materials to actually see which one is more ductile and which one is more brittle. We're gonna be trying to calculate the energy lost during fracture, and we'll also try to understand the importance of toughness of a material. The apparatus that we're going to be using is a TQ energy absorbed at fracture lab setup. We're going to be using 3 notched specimen. One is brass, another is aluminum, and the last one would be in steel. And we're going to need some instrumentation to calculate, to measure the arm length of the hammer and the angles of the hammer, angles of the hammer during and after a strike. The next part of this lecture would be the procedure you have to follow to get the results and do this experiment. And so that part will be covered during the class. I hope all of you enjoyed the lecture. I'll see you in class. Thank you.